Cool. Okay, thanks a lot for joining today. So we have here Gabriel Bender from Google Brain. So he will speak about his work on weight sharing. So yeah, the title, as you can see, is Can Weight Sharing Outperform Random Architecture Search and Investigation with TuNAS? So it was a CBTR 2021 paper. 2020, right? Not 21.
2020.
2020, yeah. Yeah, so yeah, thanks a lot, Gabriel, again, for accepting our invitation. So the floor is all yours.
Great, thanks. So I'm going to talk about a project that I've been working on recently called TuNAS, focusing on weight sharing NAS. And this is joint work with a lot of different collaborators from different parts of Alphabet. Okay, I'm having trouble. There we go. So one thing that I do want to note is that deploying machine learning models at scale is hard. If you have a promising model, there are actually a lot of considerations you need to look at before you can push it into production. There's accuracy, throughput, latency, power usage, fairness, understandability, and others depending on exactly what the circumstances are. In this talk, I'll just focus on two of these considerations, accuracy and latency. And these two are very often at odds with each other. The ability to deploy models in production is very often contingent on hitting specific latency targets. For a mobile model, you might need to run in real time, where you need to make predictions within a certain number of milliseconds in order to keep up with a video stream or provide sufficiently responsive apps. Or you might have a server-side application where you want to respond to a client's requests within a certain number of milliseconds. And even for applications where there aren't strict constraints on model size or latency, there are very often important trade-offs between size and accuracy. So one way that we can improve these trade-offs is by playing with the network architecture and revisiting some of the decisions that you've made about what kind of building blocks to use and where to use them. But trying to do this manually via trial and error can actually be quite challenging. And the reason is that there are actually a lot of little knobs that you can tune. So for instance, do I want a smaller number of more expensive operations, or do I want a larger number of cheaper operations? And there are a lot of different ways that you can actually make this trade-off. You can switch between more expensive 7x7 convolutional kernels and cheaper 3x3 convolutional kernels. You can switch between wide, expensive layers with many channels and a larger number of narrow layers with fewer channels, and so on. And each of these knobs lets you trade off between accuracy and latency in a slightly different way, and these knobs can actually interact with each other as well. So there are many different ways that you can potentially design an architecture that will get you the same latency, but potentially very different accuracies. And reasoning about these is tricky. So the value proposition for architecture search that I tend to think about and that I'll focus on in this talk is that we're trying to build out tools to help humans reason about these trade-offs. And here I'll formulate it as an optimization problem. We want to select network architecture which maximizes model accuracy subject to some constraints on model latency. And in the past few years, there have been a lot of papers that have used these kind of automated algorithms to show very impressive results. And this plot on the right, I don't know if you can see my cursor, but there's kind of the black line, which is existing systems. And then there is the red curve, which is up and to the left of it. To the left means that the models are faster, and up means more accurate. So basically what this is saying is that this is a paper making the claim, which is typical for architecture search, that our models can provide better accuracies at the same latency or at the same notion of model size, whatever it is, in this case flops, than existing systems. So this ability to push out Pareto frontiers to actually improve this trade-off can be really useful in practice. But there are a few limitations of a lot of NAS methods that I want to mention too. One is the cost of a search, and this is especially true of some of the earliest works on neural architecture search, which would actually involve training thousands of different candidate network architectures from scratch. And this step of training many different architectures can actually be quite expensive. So the mitigation that we use here, which is actually one that's become quite common in the NAS research community, is to use weight sharing. Basically, we train a single large set of model weights, and then use these shared model weights to evaluate many different candidate architectures in the search space. And this, in our case, reduces the cost of a search to a factor of within 5 or 10 of training a single network architecture, or less in some cases. I know that there are other papers that have claimed even more drastic speedups. But the important thing for this talk is that we're making the cost manageable for our purposes. The second limitation is that it's very often not clear just looking at these results, like the plot I showed you earlier, where wins come from. And there are actually a lot of potential sources, and it's really important to break these down carefully. So for instance, it could be that the authors of the paper did a really amazing job of engineering new architecture search spaces. And so any architecture that you pick from that space would be incredibly good just because that's how the search space was designed. Or it could be that you have a large search space which imposes a relatively weak prior and is difficult to navigate, but that you have a really good search algorithm which can effectively navigate and find good points in the space. Or it could be that your architectures are about comparable to what's been done in the past, but you've done an incredibly good job of finding better model training hyperparameters, which make a big difference in terms of accuracy. And all three of these are potentially very valuable contributions, but attributing them is also extremely important. So especially if you have a paper focusing on NAS algorithms, you want to make sure that you're properly attributing the wins, and that they're really coming from the search algorithm rather than other design components. Or if you're proposing a new search space, you might want to understand the trade-offs of that better. And so attributing these wins, I think for a research problem, or from a research perspective, is really important, especially because there is very often a kind of hope that if we use a certain type of algorithm, or if we switch to a certain type of space, or if we tune our parameters in a certain type of way, then we can get better results. And so when I'm looking at papers, I'm constantly thinking, okay, there are these really interesting ideas. Can I use them to improve my own system? And so this is one motivation for me for why this attribution is important. There's one shout out that I want to give to a paper, Lee and Telwakar's Random Search and Reproducibility, which I think has a very well executed analysis of some of the challenges involved here. So I want to take a step back now and list out some things that I would kind of hope that NAS algorithms would be able to do. First of all, I'd hope that they do a reasonably good job at optimizing network architectures, which means that if I feed it some reasonable search space, I'd hope that it would be able to find pretty good architectures which satisfy the latency constraints I have. Second of all, I'd like these to be robust enough that they can be used in different settings. So for instance, optimizing models for different hardware devices, optimizing for different tasks, say image classification versus object detection, and being able to work in a variety of search spaces. Ideally, even without having a very long, challenging iteration loop for users. So if users spend most of their time kind of trying to work around limitations of the algorithm and optimize for search spaces, specifically to work around the quirks of the algorithm that we give them, then that would be a sign that we really need to improve these algorithms. So robustness, I think, is a second important constraint. And finally, I would like these search algorithms to be reasonably cheap. There are two reasons for this. First of all, if we have more efficient algorithms, then we can potentially apply them to more problems. But second, even if we have the resources to run more expensive algorithms, faster search algorithms mean that we can run a lot more experiments in parallel, and we can run experiments in less time, which means that iteration times can be sped up significantly. Now, there's an important caveat here, which is that I focused on reasonably good optimization rather than perfect optimization. Perfect optimization is probably asking a bit too much. And the algorithms that I'm going to discuss here definitely are not perfect. We've actually spent quite a bit of time looking into different cases where they do have suboptimal behavior. But I don't think that these algorithms necessarily need to be perfect in order to be useful. So I want to dig into this a little bit more now, talking about some of the experiments that we've done on our weight sharing algorithm to figure out, okay, are these actually satisfying the criteria that I laid out before? One thing that we can do is to compare results found by our search algorithm followed against results found by random search in a significantly more expensive setup to figure out if the added complexity of using weight sharing algorithms actually buys us something. We started out with a reproduction of an existing widely used search space called ProxListNAS, where we already actually see a gap between what search algorithms can deliver and with weight sharing and what we can get with random search. And then we further push this to two much larger search spaces that we used to evaluate the robustness of our algorithm and to really stress test the algorithm in much more challenging problems. And there, what we see is that there's actually a drop-off in the accuracy of random search. Because these spaces are much larger, we're imposing much weaker priors, but weight sharing NAS is still able to provide high quality results in these cases. So this is kind of one way that you can think about robustness. Basically, for random search baselines, is there actually a gap between what weight sharing NAS can do with our implementation and what random search would be able to give us? Another way that you can look at this is to ask, okay, well, if we take a large search space, is it actually going to be able to recover architectures which are competitive with things that people have come up with in the past and have spent a lot of effort engineering? So for this purpose, we actually used MobileNet v3, which was optimized actually with a combination of two different architecture search algorithms, and where quite a lot of engineering effort was spent trying to improve the architecture already. We built a large search space around this network architecture, and then ran our weight sharing implementation on it to see if it could provide results which were competitive with MobileNet v3. And in this case, what we found is that the results actually were competitive. So these are two different ways that we can look at the problem of whether the search algorithms we're using are actually doing something interesting and whether they're reasonably robust. And I'll get to some others later in this talk. I do want to touch here also on search cost. So with these early algorithms where you would train thousands of network architectures from scratch, experiments were quite expensive. For instance, requiring on the order of 5 days with more than 200 TPU chips. And the weight sharing methods that we were experimenting with were around 50 times more efficient. So I think we were doing well on that axis as well. So there's one other way that we can think in terms of robustness and these results being useful, which is through the lens of collaborations with other teams in Alphabet who are actually interested in using architecture search for their own problems or for different problems than the ones we were originally thinking about. We've actually had quite a few collaborations. I cannot talk about all of them here, but I do want to highlight a few that have been announced externally. So one of these is MobileDebts, which was basically trying to build better network architectures for object detection on mobile devices like cell phones. And this was really combining two ideas. The first is that the best network architectures that we're able to find for image classification, if we just transfer those over to object detection, that doesn't actually work quite as well as if we search for new backbones from scratch on the detection task. So this problem domain of image classification versus object detection does seem to make a difference. And the network architectures you get for classification or detection are actually qualitatively different. That's one idea, that by searching on the task we care about, we can actually get better results. The second observation is that a lot of previous work has focused on optimizing either flops or mobile CPUs. And very often the operations which are most efficient for these hardware devices are going to be different from the operations which are going to be most efficient for the mobile accelerators, things like edge TPUs or digital signal processors or mobile GPUs, which are becoming increasingly common on mobile phones. So this is one interesting application which builds on the architecture search algorithms we were exploring. Another is MobileNet Edge TPU, which was actually a collaboration with folks from the Edge TPU team at Google, among others. And here the idea was basically to design network architectures which were specifically optimized for edge TPUs and provided especially good latency, accuracy trade-offs for those devices. And finally, a third project that I want to briefly mention was multi-hardware models. And the idea here is that in a lot of recent NAS works, people have assumed that we'll basically deploy a separate model for each hardware device that we actually care about. And because the Android ecosystem is quite large, there are actually a lot of different devices we need to worry about. And deploying a separate model for each one is actually something that brings with it a lot of challenges. Certain steps of the process for model deployment, like quality assurance, can actually scale, the cost can actually scale linearly with the number of devices that you want to deploy. And so deploying a lot of different models for a lot of different devices brings with it a lot of overheads. So the goal here was to revisit this assumption that we actually need lots of different devices, models for lots of different devices, and seeing if we could actually come up with a single model which was reasonably efficient across a wide variety of devices. So those are basically a few of the collaborations that we've had. And this is kind of engaging in these collaborations and working with people who want to design new architectures for their problems is another way that we've tried to build confidence in these algorithms. So now I want to get a bit into some of the technical details of this work. So next slide, okay. Weight sharing, I think that many of the people in the seminar will already be familiar with, but I want to still get into this a little bit. So again, this is coming back to this trick that we used. Instead of training many different network architectures from scratch, we would actually train a single large set of model weights and use them to evaluate many different candidate architectures in the search space. And this can drastically reduce the cost of running architecture search experiments. So what's the idea here? Let's take a very simple example. Let's suppose that we want to choose between applying a 3x3 convolution, a 5x5 convolution, or a max pooling layer at a particular position in the network. Naively, what we could do is to train 3 different networks, one with each possible operation, and then see which one has the best accuracy. But the idea behind weight sharing is to instead train a single large network where we apply all 3 operations to the same input and then add the results together. And then we can simulate a network containing, say, just a 3x3 convolution by zeroing out the outputs of the other 2 operations. So in this case, I basically replaced 3 small networks with 1 large one. But in general, in a realistic search space, we're actually going to have many different decisions that we need to make at many different points in the network. And so we can take these blocks and stack many of them on top of each other. And as the number of decisions that we need to make grows, the size of the number of shared model weights that we need to train grows linearly with the number of decisions. But the size of the search space, the number of ways that we can combine these different decisions grows exponentially. And so what this means is that we can embed a fairly large search space in a relatively compact one-shot model, which we can use to rank different candidate architectures in the search space and identify the most promising ones. So this works well up to a point, but it turns out that we run into some challenges if we want to push this even further. And there are a number of reasons to focus on larger search spaces, which we did here. The search spaces that we were eyeing at the time were things like MNASNet or especially MobileNet v3, where people were making these very fine-grained decisions about the number of filters in different layers of the network. Proxyless NAS was a very strong motivation for this work, and it was really one of the first papers that made me think that different ideas related to latency constraints and weight sharing could be successfully combined. But at the same time, the search spaces that were explored in that paper were actually pretty limited. So you have a bunch of blocks, and for each block, these are inverted bottlenecks in a mobile net style architecture. And for each bottleneck, you're essentially making two decisions. One is about the convolutional kernel size that we're using, and the other is about the hidden layer size called the expansion factor in the middle of the network. So basically, you have three possibilities for the first choice, two possibilities for the second, and so we can just enumerate all possible combinations of these two choices. There are only 6 of them, and we generate a separate set of weights for each of these 6 choices. This works well because the total number of combinations that we can, the total number of choices for any particular position in the network is relatively small, and these choices for different layers don't really interact with each other in any explicit way. But the search spaces that we were looking at were actually much, much larger. Instead of having 6 possible choices for each inverted bottleneck, we actually had on the order of 250. And so trying to enumerate all possible combinations of these choices would have made the one-shot model, the set of shared model weights that we wanted to train, prohibitively expensive. So what we did to mitigate this issue was to combine the kind of op masking or op selection metric that I showed you earlier with a second idea that we borrowed from Brock et al.'s SMASH paper, which I'll call channel masking. And the idea here is that suppose we don't actually know how many output channels a convolution should have. Then we can construct a convolution with a large number of output channels. Let's make the math easy. Let's say 100 output channels. And if we want to emulate a smaller convolution, say containing 80 output channels, then we can just zero out the rightmost 20. And so by generating a big convolution and masking out different subsets of the channels, we can actually emulate convolutions of different sizes. And this is something that can allow us to efficiently explore a range of different filter sizes. And it is something that can be successfully combined with the op masking approach that I showed you earlier. So between op masking and channel masking, we're able to explore much larger search spaces than before. So for instance, increasing the cardinality of the search space from 10 to the 20 to 10 to the 40. The magnitude of the search space gives some indication of how many possibilities we have to reason about. In terms of complexity, this is a more complex question. And cardinality is kind of one way that you can get at it, but another way that you can get at it is the size of, if you pick architectures at random, how likely are you to find good architectures in the search space simply by random chance? And this is something that I hinted at earlier, and it's something that I'll return to later. So by pretty much any metric that I can think of for measuring the size or complexity of the search space, what we're trying to do here is increase the size and really push our algorithms and see how well they hold up. So this is a bit of a primer on weight sharing. Now I want to get into a few ideas which are less common in the weight sharing scheme, but which worked well in our implementation and are contributions of this work. The first is op and filter warmup. And the idea here is that to kind of treat this in a model pruning perspective, where we actually start out by enabling every possible operation in the network at every training step when we're actually training the shared model weights. And then over the course of training, we start dropping out operations and dropping out filters more and more often. So this is a relatively simple change to our training setup, but it's one that provided substantial boosts in the performance of the search architectures in some cases. So basically, one way to interpret this is that this is actually improving the quality of the shared model weights that are used to rank and evaluate different candidate architectures in the search space. So this is one thing that we explored, and this is really a refinement and a simplification of some ideas that we worked on in an earlier paper called Understanding and Simplifying One-Shot Architecture Search. Another one that we explored here is something I'll call the absolute value reward function. And the motivation for this is that, as I alluded to earlier, in many cases, we actually have a strict inference time budget that we can use. So for instance, maybe we can spend up to 10 milliseconds to make a prediction, and beyond that, a model is just too slow to actually deploy. But precisely controlling the latency of the search model turns out to be much more difficult, especially in a weight sharing setting, than we originally expected. And there are essentially two failure modes here. The first is relatively straightforward. If the model is too large, if it runs too slowly, then it's just going to be too slow to deploy, and we need to find a way to speed it up. But going under the inference time limit by too much is also problematic, because very often we can make a model more accurate simply by scaling it up. And so if a model has a latency which is significantly lower than the inference time budget, that's a strong signal that its accuracy is going to be suboptimal, because we probably could have chosen a larger model, gotten better accuracy, and still come in under budget. So our goal, as I mentioned at the beginning of the talk, is to solve a hard constrained optimization problem. Select an architecture which maximizes model accuracy to the best of our abilities, subject to some hard constraints on model latency. But as is common for these types of optimization problems, we're actually relaxing this to a soft constraint. Basically, we're defining a single unified reward function, which depends on both accuracy and latency, and then trying to use the reinforce RL algorithm to optimize it. So when you're using reinforcement learning, there's always kind of this reward engineering question of, well, how should we actually define our reward to get good results? So here's one initial idea that we explored. This was originally proposed in a paper called MNASNet, which uses this idea in an architecture search setting without weight sharing, and it works well there, but we actually run into some issues in the weight sharing setting. The idea is that if a model's latency is below our target, then we just reward more accurate architectures and don't worry too much about latency. But if a model's latency is above our target, then we actually penalize the model depending on how far above the target it is. So the idea is that if the algorithm is consistently selecting architectures which are above the target, then we'll encourage it to reduce the inference time until it meets the target. But if it's below the target, then we don't explicitly encourage it to reduce the latency any further. So this works quite well in the original setting, but in the weight sharing setting, we actually start running into some issues. it turns out that we're introducing this extra hyperparameter beta controlling the trade-off between accuracy and latency. And we actually need to retune this value of beta quite frequently whenever we want to explore a new search space, or even when we're just making changes to the ways that the shared model weights are trained. And when we started digging into why this frequent retuning was necessary, it turns out that there are basically two failure modes. One, again, is relatively straightforward, which is overshooting. Basically, we make this parameter beta too weak, which means that we don't sufficiently penalize the model for selecting expensive architectures, which means that the latency constraints are effectively ignored or not counted strongly enough, and we end up with an architecture which is too slow to actually deploy. But the second failure mode, I think, is the more interesting one, which is undershooting. And in that mode, what happens is that we make the latency penalty too strong, which means that we penalize architectures which have latencies above the limit. And here's something very interesting happens. Ideally, what we would want is an architecture Reinforce is actually dealing with the probability distribution of our architectures. And ideally, what we would want is that it focuses on a distribution whose median is maybe just a little bit to the left of the latency limit, just slightly below the limit. But if that's actually the case, then because it's sampling from a probability distribution, occasionally it will, just by random chance, sample an architecture whose latency is above our limit. And there, because the latency penalty beta is large, we'll very heavily penalize the controller for selecting this more expensive architecture. So what happens here is that the reinforced algorithm, the controller, which is focusing on a specific part of the search space, actually becomes risk adverse. And it shifts the entire distribution of architectures that it's sampling far to the left. The logic being that it's better to sample architectures which are well below the latency limit, even if they have suboptimal accuracy, because the alternative is to occasionally sample an architecture which is above this limit and receive this huge penalty for doing so. So the net effect of this is that we end up, unless we very carefully retune beta, sampling architectures which have latencies well below the limit, but suboptimal accuracies. So what we chose to do to mitigate this issue is to actually switch to a different reward function, which penalizes both architectures which are too fast and architectures which are too slow. So the idea here is that we're effectively taking this prior that larger architectures are very often more accurate, and so we should use the entirety of our inference time budget and just baking this into the reward function. And because the reward function is symmetric, because we'll equally penalize architectures which are too fast and too slow, this reward function is actually much less sensitive to the exact value of beta, and we can get good results with approximately the right latency for a large number of different values of beta. So even though we still have this extra hyperparameter, it's one that needs to be tuned much, much less often. And so in many cases, this actually reduces the cost of running searches by a factor of around 5 because we no longer need to grid search over different values of beta. So those are some of the ideas that we've had in this work to improve accuracy and reduce the need for hyperparameter tuning. Now I want to briefly return to some of the things that I touched on earlier in the talk about whether this actually works. So there was, especially at the time that we published this paper, quite a bit of controversy about whether weight sharing algorithms could significantly outperform random search. And there were a few high-profile negative results where this was found not to be the case. But trying to understand why are we getting these negative results, there are actually a number of different things that could be going wrong. There might be a fundamental issue with weight sharing methods, which prevents these from working. Or it could be that weight sharing methods do work in certain use cases, depending on, for instance, the search bases that we're using and the data sets that we're interested in. And because this is deep learning, there's also always the elephant in the room of, is this just something that needs to be tuned very carefully before you can start getting good results? So really one of the starting out points for this work was the belief that weight sharing NAS, if we implemented it properly, could work well enough to be useful in practice. And a lot of the early work that we did was actually just trying to test this hypothesis. A few of the things that we did early on were very much centered around this. And there's also this important caveat that we want these architectures to be useful, but we have also seen a number of cases where these algorithms, while outperforming random or matching human baselines from previous work, are demonstrably suboptimal. Like we've come up with certain counterfactuals cases where we know these architecture search algorithms could be doing better. And if you're actually interested in architecture search algorithms, this is probably a very good thing because it means that there's still room for improvement, but you need to be careful about where you look because starting in a space where there's very little room for improvement, it's going to be insanely difficult to actually make significant improvements, no matter how good your search algorithm is. Whereas if you start in a space or on a problem where existing algorithms struggle, then there's potentially a lot more room for improvement. In our work, we're primarily interested in taking what was the best algorithm that we could come up with at the time, trying to tune it well, and then vetting it to the best of our abilities. One of the things that we explored was comparisons against random search, where we were really using a sequence of increasingly large and complex search spaces to stress test our algorithms and see how they would hold up with weaker priors with a lot more possible choices to make. And also comparing these against known good results that had come up and been obtained using much more expensive algorithms in the past and seeing if we could provide competitive results there. And so for both of these sets of tests, I'm actually quite optimistic that weight sharing can be useful, at least in certain settings. So this is, if I think about it as a math major, this is kind of an existence proof. It doesn't mean that weight sharing will always be useful or that it's even always the best choice, but it is a very strong indication that it can be useful in certain cases. So that's pretty much everything that I have to say. We believe that weight sharing NAS can be useful in some cases, that it can outperform simpler approaches, and that the complexity of these methods can be justified. And probably the strongest indication that we've seen in this direction is by working with collaborators on these downstream applications using NAS in different interesting ways. Okay, thanks a lot.
Okay, thank you. Stop.